In the previous lecture, we discussed quantum computers that are based on photonics or on superconductivity. There are also alternative proposals how to create physical implementations of qubits. So these alternatives include quantum dots, these are based on semiconductors. So then there are ideas how to use nitrogen atoms in a diamond crystal. So we have a diamond crystal that is made of the atoms of carbon, and then we insert in this diamond imperfections where we replace carbon atoms with nitrogen atoms. And then there is a way how to create a qubit out of this imperfection. And so there is also any-ons or topological quantum computing. Today's lecture will focus on any-ons. In nature, all elementary particles split into two classes. So we have two classes of particles. There are bosons and there are fermions. What is the difference between these two types of particles? Suppose we have n identical particles. So where even all quantum numbers associated with these particles are the same. So for example, all these particles have the same spin state, and the only that is different for them is the location. We know that a quantum system is described by its wave function. So we have a quantum state of this. So if we ignore all other quantum numbers, so then we will have a function of variables x1, x2, xn, where each xj belongs to R3 and controls the position of the jth particle in this ensemble. The wave function is complex valued, and it leads to probability density. So this means that the probability of observing this ensemble in region D, which is inside R3 cross R3 and copies. So this probability is given by the integral over D of absolute value of psi of x1 xn squared, so dx1 dxn. So this wave function describes how likely to detect this combination of particles in the prescribed areas of the space. And typically, this wave function decays to 0 when any of the xi's goes to infinity. The difference between bosons and fermions is in the behavior of their wave functions. So for bosons, the wave function is symmetric. So this means that if we interchange any two variables, xi and xj, then the value of the wave function will not change. So it will be the same as psi of x1, xi, xj, xn. Whereas for fermions, the wave function is antisymmetric. So if we interchange two variables, then the wave function will switch the sign. So we have minus psi of x1, xi, xj. As a consequence, we get that for fermions, if we take the limit when xj approaches xi of psi of x1, xi, xj, so this limit is going to be 0. This means that if we have two fermions in exactly same quantum states, then the probability of observing these two fermions very close to each other is negligibly small. Of course, if quantum states of fermions are not the same, then this limit need not to be equal to 0. And in particular, two electrons with opposite spins may occupy the same orbital in the atom. The nature of these wave functions determines statistical properties of the particles. So, for example, when we count how many particles can occupy a certain energy level. So in this count, it's important whether these particles are bosons or fermions. It turns out that this approach to wave functions is a bit too simplistic. And what happens is that topology may affect wave functions. This has been observed in Bohm-Aharonov effect, which is the following. Suppose we have a tube inside which we have the flux of a magnetic field, and we have an electron outside of this tube. If we move this electron in the orbit around this tube, then it turns out that the wave function of this electron will acquire a phase shift. So it will change from a wave function psi to wave function e to the I theta times psi. And this phase shift theta is determined by the flux of the magnetic field in this tube. So here at no time, this electron will enter the magnetic field. It only goes around the flux of the magnetic field. This example shows that the value of the wave function cannot always be described in terms of purely the coordinates, because at the beginning and at the end of this process, this electron is in the same point. What matters here is the topological nature of this exchange. So, for example, if this electron goes around the same circle but not enclosing this tube with magnetic flux, then its wave function will not change. This suggests that when we classify particles, we look not merely on the fact of the exchange of two particles, but also at the topological nature of that exchange. In three-dimensional space, these topological considerations do not play a major role, because if we have two particles and one particle circles around the other, then this loop can be contracted in three-dimensional space by never crossing the second particle. So we just take this loop and lift it and pull it towards the first particle. However, the situation is very different in a two-dimensional space. And the difference here is that if we take R3 without a point, then this space is simply connected. And thus, any topology of the exchange of two particles will be equivalent. Whereas if we take R2 with deleted a point, then this space is not simply connected. In R2, so if we have two particles and one particle loops around the other, then this loop cannot be contracted inside R2 without crossing the second point. But in R3, such a loop will be contractible because we can take it over the second point. This explains why in our three-dimensional space we have just two types of particles, bosons and fermions. But if we lived in R2 instead of R3, then we would have a possibility for more exotic behavior of elementary particles. And this brings us to any-ons. Suppose our particles live in a two-dimensional world, and we want to look at the exchange of two particles. So let's make a picture. So here we create a time axis. So this will be time equals 0, and we want to look at evolution of this world to time equals 1. Here, if we want to make a picture of a clockwise exchange of the particles, then if we plot it along the time axis, we get the following picture. One particle will have this trajectory, and the second particle will go behind it. This process is called braiding. And it's clear that topologically it makes a difference whether we make this exchange in clockwise direction or in the counterclockwise direction. So any-ons are particles in a two-dimensional world whose wave function changes by the phase shift of e to the I theta for a clockwise exchange of two any-ons. And if we make a full clockwise exchange of two any-ons, then the phase shift will be e to the 2I theta. The behavior of any-ons is quite different from the behavior of bosons and fermions. If we take two bosons or two fermions and we make full 360-degree exchange of these two particles, then the wave function will not change. However, for any-ons, a 360-degree exchange will change the wave function of this ensemble of particles. The name of this class of particles is composed of the words any and ons. Right? So this means that the phase shift here can be arbitrary, but fixed for a given type of the any-on. Let us construct some examples of two-dimensional wave functions. So here we have an R2 with coordinate system xy. And what we do, we replace two real coordinates with a single complex coordinate. So we introduce z, which is x, plus iy. And with this, we can construct complex valued wave functions. And so, for example, for bosons, the wave function can be written in the following way. So we take psi. So now we have z1, zn. So we have n particles. And what we do is we take a symmetric polynomial in variables z1, zn, and multiply it by the exponential of minus sum, k goes from 1 to n, of norm of zi squared. This exponential factor is inserted to ensure that the wave function decays fast enough at infinity. And here we have, so p of z1 through zn will be a symmetric polynomial. A polynomial which is not changed under the permutation of variables. For fermions, we construct wave function in the following way. So we take psi of z1 through zn. So we add an extra factor. So this will be the product over I less than j from 1 to n. And here we put zi minus zj times the symmetric polynomial times the same exponential. And so here this is again symmetric. And the first factor will ensure that our wave function is antisymmetric. So if we interchange two particles, then the sign of this fermionic wave function will change. For any-ons, we can construct wave functions in a similar fashion. So if we take theta to be a rational multiple of pi, so pi times n over m. Here we will take psi to be the product over I less than j between 1 and n of zi minus zj to the power n over m times the symmetric polynomial times the exponential. This anionic wave function is much more delicate. The reason for this is that complex valued mth-root function is multivalued. So we should be careful even when we interpret the value of the function psi. If we write the complex number in the polar form r times e to the I alpha, then if we want to extract mth root of this, then this has several values. And these values are mth root of r as a real number times e to the I alpha divided by m, but also mth root of r e to the I alpha divided by m plus 2 pi I divided by m. And then the next one will be mth root of r e to the I alpha divided by m plus 4 pi I divided by m, and so on. And in total, so mth root of a complex number has m different values. Geometrically, this means that the mth root function over complex numbers has m branches. And when we specify a particular value of this wave function psi, then we should also specify the branch of this mth root function that we are taking. And it is well known for the mth root complex function that when we make a full circle in the complex plane, then we lift from one branch of this function to another, and we acquire an additional phase of 2 pi I over m. And so for each revolution around the origin, we get an extra factor of this form. For this reason, when we look at exchange of particles for this wave function, then what will be happening is that we will be traveling from one branch of this function to another, and the effect of such an exchange will be an extra factor that will appear at the function psi. And the phase shifts that will appear in this instance are rational multiples of pi. So these are pi times n divided by m. Another point that we can appreciate with this wave function is the phase shift that we acquire depends not only on the mere exchange of two particles, but on the specific trajectory of this exchange. So this expression will capture also the topological consideration of the exchange of particles. Now, let us do the reality check. Since we live in R3, there can be no anionic elementary particles. But what we could have anionic quasiparticles. What are those? A typical example of a quasiparticle is an ocean wave. When we look at the surface of the water, we can clearly identify waves as individual entities. Yet, when these waves travel great distances, there is no significant transport of mass apart from the occasional surfer that this wave can catch. So this means that we cannot say that a wave is a collection of molecules of water. Rather, a wave is an excitation in the collection of molecules of water. At any particular time, different collections of molecules of water compose the same wave. The same is with quasiparticles in general. Quasiparticles should be understood not matter per se, but rather an excitation in the matter. We can look for quasiparticles in two-dimensional quantum fluids. For example, if we have a two-dimensional film of free electrons, there is a theoretical possibility for any-ons forming as quasiparticles in such two-dimensional quantum fluids. So far, we do not have 100% solid evidence for the existence of any-ons. However, in certain experiments, there is evidence pointing towards the existence of such exotic states of quasiparticles. In order to understand quasiparticles better, let us consider the following two-dimensional spin model, which is called the Toric model. In this model, we place spin 1/2 particles at the vertices of a square lattice. The space of states for this model will be a tensor product of spaces Vij, where ij are the points on the square lattice, and each Vij is just a two-dimensional complex space. In order to make this space finite dimensional, so we let I and j run in a finite set from 0 to n minus 1. And we consider the integer n to be even. What we're actually going to do is we're going to identify row 0 in this lattice with row number n, and the column number 0 with column number n, effectively imposing the following periodicity conditions, that if we take a lattice point I plus n j, then this is the same lattice point as ij, or the same point as I j plus n for all I and j. Geometrically, identifying the top row with the bottom row means folding the space and forming the cylinder. Next, when we identify the left side of the cylinder with the right side, then this means that we are folding the cylinder and self-enclosing it, and then we're getting a torus. Folding a cylinder into a torus in a three-dimensional space requires stretching. However, in a four-dimensional space, this can be done even without stretching paper. Mathematically, of course, we don't need to do any folding, and we just identify the opposite sides of our square. Next, we're going to paint the squares of our lattice, forming a checkerboard pattern. We mark half of the squares in our lattice as red and the other half as green. And the rule is that if we have a square, the square is formed by the vertices ij, I plus 1j, I j plus 1, and I plus 1, j plus 1. And if I plus j is even, then we mark this square as red. And if I plus j is odd, then we mark the square as green. And we have chosen n to be even to make sure that this checkerboard pattern is compatible with the periodicity imposed by our toroidal structure. Our space of states is the tensor product of n squared copies of a two-dimensional complex space. And next, we're going to write down the Hamiltonian for this system. Our Hamiltonian will be minus the sum over r red squares of operators AR minus the sum over g green squares of operators BG. What are these operators, AR and BG? If we have a square with the bottom left corner marked as a vertex ij, then operator AR for this square is the product of Pauli matrices. We have sigma x at location ij times sigma x at location I plus 1j times sigma x at location I j plus 1 and sigma x at location I plus 1 j plus 1. For green squares, instead of taking sigma x, we're going to take sigma z. So BG is the product of sigma z at location ij times sigma z at location I plus 1j times sigma z at I j plus 1 and sigma z at I plus 1 j plus 1. In our model, for each lattice point ij, we have a two-dimensional complex space attached to that lattice point. And we have Pauli matrices acting on these copies of two-dimensional complex space. So operator sigma x ij is the Pauli matrix sigma x acting on the tensor factor that corresponds to the lattice point ij. And for all other tensor factors, the operator sigma ijx acts as identity. Since all AR operators are made of sigma x Pauli matrices, all such operators will commute between themselves. And likewise, all BG operators will commute between themselves as well. What's less obvious is that all AR operators will commute with all BG operators. This is not so trivial because the Pauli matrices sigma x and sigma z do not commute. Instead, if we have two Pauli matrices acting on the same two-dimensional space, then we can easily verify the following relation, that sigma x times sigma z is equal to minus sigma z times sigma x. Now let us understand why this commutativity holds. So we take two squares, a red square and a green square, and we attach operators AR and BG corresponding to these squares. Now, if these two squares have no vertices in common, then these two operators will surely commute. Because if AR has operator sigma x at location ij, the BG operator will have the identity matrix at that location, and sigma x will commute with the identity matrix. The only non-trivial case that we need to check is when the red square and the green square are neighbors. So this means that they share common vertices. But then from geometry, it's clear that if we have two neighboring squares, a red one and a green one, then they will have exactly two vertices in common. Then in these locations, so sigma x operator and sigma z operator will not commute. Rather, we will get a negative sign when we try to push one operator across another. But we have two vertices in common, and so this negative sign will occur twice. And then these two negative signs will cancel, and then we obtain commutativity of AR with BG even for the neighboring squares. What we would like to do is to compute the energy spectrum of this model. So for this, we need to find eigenstates and eigenvalues of the operator H. So we have H psi is equal to E times psi. So here psi will be the energy eigenstate, and E is the corresponding eigenvalue, is the energy level corresponding to that state. In particular, we would like to understand what is the ground energy level, so what's the lowest energy in this model, and what are the excited states. The commutativity property for operators AR and BGs is going to help us a lot. So here we point out that all these operators are self-adjoint. And now we have a collection of commuting self-adjoint operators. Linear algebra teaches us that commuting diagonalizable operators are simultaneously diagonalizable. And self-adjoint operators are, of course, diagonalizable. So this means that we have a basis of the space W of this huge tensor product, where each operator AR and BG is diagonalizable. So this means that we have a basis of this tensor product space W, in which every basis vector is an eigenvector for all of these operators, all of ARs and all of BGs. So these operators will be diagonalizable in this basis. And then, of course, operator H will also be diagonalizable in this basis. So this means that all the basis vectors are going to be eigenvectors for the Hamiltonian as well. Let us try to understand the possible spectrum of eigenvalues. We know that each Pauli matrix could have eigenvalues 1 or minus 1. Then it's clear that operators AR and BG also will have eigenvalues 1 and -1, because these would be the products of eigenvalues of the corresponding sigma matrices. Then what would be the lowest energy level in this system? It is clear that we get the lowest possible eigenvalue for the Hamiltonian H, where each of the operators AR and BG has eigenvalue of 1. In this case, we get that the ground state energy is E is equal to minus n squared, since each square contributes -1 towards the eigenvalue, and on this torus we have n times n squares. Next, let us discuss the ground level eigenstates. Let us work in a basis of eigenstates for sigma z matrices. So this means that we are choosing a basis of W that consists of tensor products, where each tensor factor is either spin up with respect to z, right? So this will be in location ij, or in this location ij will have spin down with respect to z-axis. And now in each lattice point, we choose either spin up vector or spin down vector. Then such vectors will be eigenvectors for every sigma ijz matrix, and these will be eigenvectors for BG operator. We would like to select only those basis vectors that have eigenvalue +1 with respect to each operator BG. We say that a basis state psi has a vortex at G if psi is an eigenstate for BG with eigenvalue -1. Now, what does this mean? So this means that psi has an odd number of down z vectors at the vertices of green square G. Now, for each basis vector, we have either an up z vector or a down z vector placed at each vertex. Now we take a green square, so there are 4 tensor factors that are attached to the boundary points of this square. And if we have an odd number of them, so 1 or 3 vertices with down z vector, then of course such a square will have eigenvalue -1 with respect to BG. And to get a ground state, what we want is we want all BG operators to have eigenvalue +1. So we conclude that the ground state has no vortices. So this means that it is a linear combination of basis state vectors such that each term in this linear combination has for each green square an even number of down z vectors attached to these vertices, and thus also an even number of up z vectors attached to these vertices. Next, let us analyze AR operators. And again, a ground state must be an eigenvector for each AR with eigenvalue +1. The difficulty is that the basis of up z and down z vectors is not the eigenbasis for AR, because sigma x Pauli matrices will have a different basis of eigenvectors. If we take a basis vector which has up z or down z tensor factors at each lattice vertex, then what AR operator does, it would flip the up z and down z factors at each vertex of the red square, because sigma x matrix looks like 0, 1, 1, 0, and that's what it does to up z and down z vectors. So sigma x applied to up z is equal to down z, and sigma x applied to down z is equal to up z. So we see that AR will flip up z and down z tensor factors at these 4 locations that correspond to the boundary of the red square. Now, in order to construct eigenvectors for operators AR, we're going to use the following trick from linear algebra, that if operator A has only 2 eigenvalues, -1 and -1, then operator 1/2 identity plus A is the projection to lambda equals +1 eigenspace. Indeed, if we apply this operator to -1 eigenvector, then A will multiply it by -1, but identity operator will multiply it by +1. And as a result, this operator will kill every -1 eigenvector. And if we apply this operator to +1 eigenvector, then identity will contribute 1, A will contribute 1, and taken with the factor of 1/2, we see that every +1 eigenvector is preserved by this operator. So this operator preserves +1 eigenvectors and kills -1 eigenvectors. So this means that this operator is the projection to +1 eigenspace. If we have a state which is -1 eigenstate for AR, so AR psi is equal to -psi, then we say that psi has a charge at red square R. And then we see that the ground state has no vortices and also no charges. So that will ensure that the ground state has eigenvalues +1 with respect to each AR and BG operators, and the total energy of the ground state will be -n². Now let us show how we can construct ground states for this quantum system. We start by taking psi to be a basis vector. This means it's a tensor product of either up z vectors or down z vectors with no vortices. So that is, for each green square, we have an even number of up z vectors. So for example, as psi, we can take a tensor product where each tensor factor is up z. This psi is not going to be an eigenvector for AR operators. But what we can do is we can project it to the +1 eigenspace for all operators AR. We take the product over all red squares of identity plus AR. And the number of factors here is the number of red squares, which is n²/2. So we put an extra factor of 1/2 to the n²/2 and apply this to the ground state, to the basis vector with no vortices. And then this projection operator will ensure that the resulting vector will have no charges either. And so this will give us the ground state with energy being equal to minus n squared. In fact, it is possible to show that the ground energy level is degenerate. So this means that it is not one-dimensional, and it has dimension 4. This means that the basis vectors with no vortices will produce 4 different linearly independent projections to the space of ground states. And we also see that the energy spectrum for this problem consists of integer values, and these integer values go from minus n squared to plus n squared. And so we have plus n squared eigenvalue when we have a state that has a charge and a vortex at each red or green square. Next, we're going to discuss excitations in this model. So that is how we can take a state at the ground energy level and then obtain from it another state of a slightly higher energy. Let us take our lattice and let us construct a path L connecting the centers of adjacent red squares. And for each such a path, we construct a charge path operator, which will be PLC, so C stands for charge, which is the product over ij. So these will be vertices in the path L. So these are the blue vertices of our lattice through which this path is going through. And here we multiply this by sigma z ij. What are the properties of the path operator? Well, since this path operator is composed of sigma z matrices, it clearly will commute with operators bg. And this means that this operator will preserve the eigenvalues of bg. So this means that this charge path operator preserves absence or presence of vortices. So if we have a green square with a vortex and we apply the path charge operator, the resulting state will also have a vortex at this square. Or if there is no vortex at green square, then by applying the charge path operator, we get another state with no vortex at the green square. Now let us understand the relationship between the charge path operator and operators ARs that correspond to red squares. For red squares in the middle of the path, we see that these squares will have an even number of vertices that will belong to the path. However, for the red square at the beginning of the path and at the end of the path, we see that we have an odd number of vertices that belong to the boundary of the square and lie on the path. So recalling the relations that we already mentioned, that sigma x ij with sigma z ij is equal to minus sigma z ij times sigma x ij. And the path operator is made of sigma z factors, whereas AR is made of sigma x factors. So this means that if R is either the start or finish of our path, then we will have that AR with the charge path operator is equal to minus the product PCL with AR. Whereas for all other values of R, we have the commuting property. The path operator will commute with AR. Now we apply linear algebra, that if we have two operators that anti-commute, so AP is equal to minus PA, and V is an eigenvector for A with eigenvalue lambda, then it is easy to check that the vector PV has eigenvalue minus lambda with respect to A. This means that the charge path operator applied to a ground state will create charges at two red squares, at starting and finishing red squares. And thus, it will increase the energy of the state by 2. We can also apply this construction to vortices. So let L now be a path connecting centers of green squares. And consider the vortex path operator, so which will be the product over ij on this path of sigma x ij. Then, in the similar fashion, we can see that the vortex path operator applied to a ground state will create vortices at two green squares. If we apply this path operator to a state that already has vortices at the start and at the finish squares of this path, then this path operator will annihilate these vortices. And if we apply this path operator to a state that has a vortex at one square but not at another, then this path operator will move the vortex from one end of the path to another. We see that charges and vortices become quasi-particles in this system. And what we can do now is we can create charges in pairs, and we can annihilate charges in pairs using path operators. And the same with vortices. So vortices can be created in pairs, can be annihilated in pairs, and also we are able to use these path operators to move charges and vortices from one location to another. The total energy of the state is determined by the number of charges and vortices that it has. Finally, let us exhibit a non-trivial topological behavior of these quasiparticles. Let us consider a loop that connects the centers of red squares, and we consider a charge path operator for a loop. So L is a loop. Then it turns out that we can factor this operator in the following product. So it's a product of over green squares inside the loop of operators BG. So recall that BG operator is a product of sigma z matrices, just as the path operator. So it's sigma ijz times sigma I plus 1 zj times sigma z I j plus 1 times sigma z I plus 1 j plus 1. So inside this path in this picture, we have 3 green squares. And we claim that the product of sigma z operators along the path and the product of sigma z operators at the boundaries of these squares are the same. Well, the points involved are not quite the same, because, so for example, there is this point and there is this point that do not belong to the path. But these points inside the path will belong to 2 green squares. And then the corresponding sigma matrices will cancel, because we have the property that sigma matrix squared gives us identity. And then after these cancellations at these 2 points, we will see that the factorization of this product of BG operators is the same as factorization of this loop path operator in sigma z Pauli matrices. The physical interpretation of the loop path operator is taking a charge and moving it along the loop, so returning to the same red square. Or if we don't have a charge at the corresponding red square, then we can interpret it that we have a hole at that red square, and then we are moving a hole in a closed loop. Now, suppose we take a state psi that has a single vortex inside the loop. So, for example, in one of these green squares inside the loop, we have a vortex. So then what will happen? So what will happen if we apply this charge path operator or loop operator to this state? Now, by this formula, so this is the product over green squares inside the loop of BG operators. But the state has a single vortex. So this means that one of these factors will multiply this state by -1, whereas every other factor will have psi as a +1 eigenvector. And so what we see is that this product applied to psi, because of a single vortex, will give us -psi. The physics interpretation of this calculation is the following, that by moving a charge in a closed loop, we do not create or annihilate any quasiparticles, so that is charges or vortices, but a state with k vortices inside the loop will experience a phase shift with a factor of -1 to the power of k. This phenomenon is very similar to Bohm-Aharonov effect, where moving an electron along a tube with a magnetic flux will change the phase of state of this electron. So the same observe here. So when we move a charge around the vortex, the phase of the state will change by a factor of -1, which is e to the pi I. So the important takeaway from this story is that in the toric model, we observe interactions between quasiparticles of a topological nature.